That's all in the reference manual and it's pretty easy to understand. Or if you just want a more precise explanation of exactly what some tactic that you've seen does, you can find that in the reference manual. Okay, so that's what the reference manual is good for, basically. You can find pretty good documentation of a lot of things just by looking in the standard library. So just kind of getting the source code of the standard library and grepping around a little bit will teach you a lot about how things work. Another good thing to know about internally is this search about command. So if you say to the top level, and there are ways to do this through both of the IDEs, you can give a command, search about foo, and it will find you all of the theorems that have anything to do with foo. And sometimes that's a huge long list and it's not useful, but often it's just a page or two, and then you can just scan through and find the one that you can't remember the name of. And there are more sophisticated versions of it where you can write kind of regular expression, like not exactly regular expressions, but you can write a template that says, you know, find me theorems that have this kind of structure in them. Okay, let's try this little theorem. So let's prove from P, not P. So I'll give you intros for free. So we've got P and we want to prove not P. How shall we do it? So I often find when working with, especially at the beginning, you'll find it less necessary to do this later on, but when you're first getting started, whenever I see something involving a negation, I like to just get rid of the negation and view it as an implication involving false. Because then it often makes it clearer what needs to happen. So how would we do that? I almost gave you a hint. So unfold, and what's it called? Not. So unfold not tells us what we actually have to prove. Oh, well then it's easier to see. So how should we kind of obviously proceed? Just looking at the form of things. Another intros, because what's at the bottom of the screen is a hypothetical goal. Okay, so now we've got a hypothesis that P implies false, and the goal is false. So apply looks like a good way to proceed. So apply H0, and now we need to show P, but we have that as an assumption also. Yeah. And since the proof was just a bunch of intros and applies, the proof object is a very simple Lambda term. All right. Inequality is just negated equality, so nothing very fancy there. The slightly fancy thing is existential quantification. This is not too fancy. It's just, in fact, for you higher order functional programming experts, should not be very fancy at all. But it takes a little bit to internalize the definition. So here's the actual definition from the library. It says, so existential quantification, the existential quantifier, is a family of propositions parameterized by two things, by a type and by a proposition parameterized over that type. Okay, so let's pass on to the constructor. So xintro, so the one way of proving an existentially quantified proposition is we have to give two more pieces of data. we have to give a witness, which is an element of the type X, and we have to give evidence that P, the proposition that's being existentially quantified, holds for X. Okay, so looking at the first line, X is the type of the witness. So this is for some number. So X there is number. And then P is the proposition about numbers in which X may occur. So that's the parameterization over X. Yes? Well, so the for all is because the introduction form for the existential quantifier, which is what we're defining here, takes two things. It takes a witness and it takes a proof about that witness. So it has two arguments. Remembering that in Coq there really is only one function space, the pi space, the dependent function space. So those are both. So kind of every argument to a constructor is always a pi. Here we need to explicitly write it as a pi, which we notate concretely as the upside down A. So we need to notate it as a for all because we need its name in the type of the second argument to the constructor. Right? So this constructor takes two arguments, a witness and evidence for that witness of P. And the for that witness part is the reason that we need a for all rather than just an arrow. Other questions? Okay, and then we can define standard notation for existentials using the Coq notation mechanism. And you don't really need to understand exactly how all of this works. There's a little bit of fussing around with implicit argument synthesis and things like that. It's not too important. Just a second. It's not too important exactly how it works. What is important is that it allows us to write existential quantifiers in the standard notation. Yes?
It does not mean that the property has to hold for every value of type X, right? But I have to give it as
correct. Yes, thank you. So this is not saying I have to provide a proof that for all witnesses P holds of that witness. This is saying that the type of the constructor is for all witnesses P of witness implies exists XP. Okay, so the constructor can take any witness as an argument. But in order to apply the constructor, we just need to provide one. Thank you. Okay, so now to introduce an existentially quantified proposition, to make a proof of it, we can use apply. So for example, to prove that statement at the top, we say apply ex intro, the constructor. And now we have to say with witness is 2. Why do we have to explicitly say that? Why can't Coq work it out? It's not in the conclusion. So let's look at the type of ex intro again. So remember, apply just unifies the goal with the conclusion of the thing that you're applying. The conclusion here is exists xp, and that does not have witness in it. Okay, so simply by doing that unification, we're not going to find out the witness. And that makes perfect sense because the witness, just intuitively, is something that, that has to be carefully figured out and may be hard to figure out. So we wouldn't expect unification to just automatically, magically derive it. Okay, so we say apply X intro, explicitly giving the witness. The unification mechanism works out the type X and the proposition P that we're dealing with, but it can't get the witness. As a shorthand, instead of saying apply X intro with witness equals, you can just say exists witness. So exists E means the longer thing above. And this is one place where the typesetting of the HTML version of the notes is a little bit awkward. So it's just doing simple string replacement. So unfortunately, that exists tactic also gets typeset as backwards E. Sorry about that. Okay, and then conversely, if we have an existential hypothesis and we want to use it, how do we get the juice out of it? Inversion. Same way we get the juice out of any inductively defined proposition. So if you have an existentially quantified thing, you can say inversion, and that will dump into the context a variable called witness and a proof of P for witness. Usually, having it named witness is kind of awkward. So this is a case where I always use the with variant of inversion, the as variant of inversion to explicitly choose the name of the variable that's going to be the witness. Okay? Equality, we've seen in Bob's lecture, and basically what happens here is pretty much the same. So equality is an inductively defined type. I'm calling it EQ prime here just to distinguish it from the one that's built in. But this is the definition. This is the built-in definition. So EQ is an inductively defined proposition. It has one constructor called refl equal. And okay, there's one subtlety here that I should explain. If you look at the first line of the definition of EQ prime, you'll see that there's a colon there, and there are some things on the left of the colon and some things on the right of the colon. And this is something that we've seen before, but I haven't explained it yet, so let me do so now. When we're defining an inductive family of things, that family is maybe parameterized over several things in general. And we can place those parameters either to the left of the colon or to the right of the colon. And it means slightly different things. So here is an interesting case because this definition has three parameters, big X, little x, and another little x. Sorry, big X, little x, and another instance of big X, namely the type that things are equal at and the two things that are equal. Right? So the little x and the thing that we didn't give a name to, let's call it little y for the moment, little x and little y are the things that we're saying are equal, and big X is their type. Now, when you put things on the left of the colon, they're called uniform parameters. Why? Because they don't vary from one constructor to another. So for example, in the definition of the list data type, the type X of the elements of the list went to the left of the colon. It's a uniform parameter in the sense that all of the constructors of the list type are building lists with the same type of elements. Okay, so the things on the left of the colon are uniform parameters to the inductive definition. The things to the right of the colon, that is the x arrow, is another parameter, right? Because, so strictly speaking, pedantically speaking, what we're defining here is a family of parameterized propositions of type x arrow prop, parameterized by two more things. So it's a parameterized family. So the first two parameters are uniform, and the last parameter is a non-uniform one. What do I mean by non-uniform parameter? It's the thing that varies in, for example, a GADIT, a generalized abstract data type.
Well, I think I understand correctly. So if you prime takes a type and it takes one argument and returns a function.
Right.
But I don't see the difference if you put them on the left or on the right.
Okay, so the difference is two things. If you put it on the left, then you don't have to say it in the types of the constructors. If you put it on the right, in general, you do have to say it in the types of the constructors. Here it happens, EQ is a particularly funny special case. In general, if you have something on the right of the arrow, there's going to be a for all at the beginning of the type of each of the constructors. This is confusing. Let me either make it better or make it worse by skipping ahead a little bit and showing you the simply type lambda calculus. Here is the typing relation for the simply type lambda calculus. Notice that here all of the parameters are non-uniform. Why? Because in different typing rules, in different constructors for this relation, they vary. Right? So the gamma, the term, and the type that are being put into this three-place relation by each of these rules are different for each of the rules. So we make them into non-uniform parameters. And now notice that at the beginning of each of these constructor types, there's a for all. Binding, well, all of the ones that we're going to use in the conclusion type, and sometimes some other ones. Does that help? Okay. Yep.
Is there any in the type theory what's going on here, or is it just syntactic things for what you need to write there?
Exactly. The main difference is in the induction principle that gets generated. So let's see if this is correct. I believe that you can always make parameters less uniform. Right? So you can always take uniform parameters and move them to the right and add some quantifiers. The effect of that is the induction principle that's generated is going to be more complicated. It's going to have quantifiers in it. Because effectively, if you think about it, the uniform parameters are kind of arguments. If you think about the type of list, for example, where is it? Let's see, in poly.v. Here are our polymorphic lists. Okay, so x is a uniform parameter. That means, intuitively, this is a function from types x to inductively defined families. That means that for each of those inductively defined families, the induction principle doesn't need to do any quantifying over x. X is just a constant in each of the induction principles for each member of the family. Whereas if we moved the x to the right-hand side of the colon, then the constructors would have quantified types, and the corresponding clauses of the induction principle would have to mention those quantifiers.
Of course, it makes what we want to prove easier or more difficult, but does it change what we're able to prove?
No, and it shouldn't change what we're able to prove. So if there's a parameter that's uniform, we can move it from the right to the left and get a simpler induction principle from which we should be able to prove all the same things, and vice versa.
Don't you have like a theorem or a lemma saying whenever we have this induction principle, then we can generate the other, and then we don't need to worry about this thing?
So I'm sure there is such a theorem, but it's a theorem about Coq rather than a theorem in Coq. That is to say, in Coq you can certainly witness every instance of that theorem. That is, if you define the inductive type one way and you actually want the induction principle the other way, you can prove the new induction principle from the old one. But Coq isn't going to do that automatically.
So do I have to do it for each instance, or can I just have a theorem?
You would have to do it for each instance.
Okay, so we cannot quantify like overall. I mean, so in general, saying something like if I define the inductive type and yeah, I have the parameters on one side, then I can generate the inductive principle.
So the thing that you're saying is true. So if I have an inductive definition of this form, then there's another one of this form, and the induction principle for that one follows from the induction principle for this one. But that fact is not internalizable in Coq, I believe.
Question?
Yes?
What happens to the universe levels? What if you move the uniform parameter x to the right?
That's a good question. I think nothing, but we should check. Okay, but let's not check together because I want to. We've spent enough time on this, I think. This is an example. So one thing that I don't like about Coq for teaching purposes is it has quite a lot of these kind of deep waters that take a little bit of type theoretic sophistication to really grasp, and where you actually do need to kind of have a grasp of it in order to be a power user of Coq. You can't get too far without kind of understanding this stuff about uniform and non-uniform parameters and things like that. And it makes it a little complicated for if what you want to do is just get to the point where you can start talking about programming languages, which is the point we're trying to get to. It's a little annoying to have to go through these deepish explanations. However, you will find that even if it's kind of confusing now, things like this will quickly start making sense. There are a few other things that may take more time, but I'm going to try to sidestep them. Okay, that's enough about equality. I think let's skip to here, relations as propositions. So the last observation to make, and then we really can go on and begin talking about programming languages. The last observation to make is that we've been dealing with propositions parameterized by one thing. Those are properties. We can just as well parameterize propositions by two things, by three things, by 10 things, and those are inductively defined relations. So here is another slightly interesting inductively defined relation. This is the less than or equal relation, and again, it's slightly interesting because it takes two parameters, and it treats one of them uniformly and the other non-uniformly. And the reason for that is simply to get a nice looking induction principle. So something that you may want to try is changing that uniform parameter into a non-uniform one. You still get a perfectly usable induction principle, but it's a little more confusing to look at. This one is, to my mind, the natural induction principle for less than.
why define so we assume that the
Mm-hmm.
so
Oh, I see. Yeah, so why not use BLE NAT to define less than as in a computational way instead of the inductive way? We could also do that. And in this case, once again, they're both good. Other questions?